Ladies and gentlemen, presenting Miroslav Bicanic, an ML engineer and Cross AI, DO. His pioneering work, his computer-controlled gesture, led into the AI-powered application for gesture-based mouse control. He further contributed to Alano, an NLP annotation platform, and showcased his experience at the ECL conference in 2023. With over 2 years at Cross AI, Miroslav specialized in ML system design and real-time ML. Today, his talk, Under Pressure, Applying ML in Real Life, he'll address challenges in real-time ML applications. Please welcome Miroslav Bicanic.
Hi, everyone. First of all, thank you for coming to my talk, and thank you for the introduction. My name is Miroslav Bicanic, and I came here today to share with you a little story called Under Pressure. Now, unfortunately, it has nothing to do with Queen, and it's about real-time machine learning. It's also a story about a journey that we at Cross AI took to create a real-time machine learning platform. So, as every other story, we first need to set the mood with an introduction, like establish the basics, like what real-time machine learning even is, how it works, what it depends on, and so on. So I would like to start things off with these two quotes from the same 2023 article, which estimates that by 2030, the data streaming market will be over 70 billion, and the ML market will be over $200 billion. Now, these huge numbers indicate that there is something promising in these markets. Basically, there's more and more data every second. And the sooner and better you can process it and make it meaningful, the more informed your decisions can be. And this brings us to real-time machine learning, or RTML for short. So in the picture, you can see a crossroad, because like every other interesting thing, RTML is also at the intersection of two different fields. In this case, these are data streaming and machine learning. So the idea is the following. In the beginning, there was data, and people were processing it manually to extract knowledge, notice patterns, make decisions, and draw conclusions. Eventually, there was a problem, though. There was too much data for humans to handle manually, so we decided to identify the logic behind the data. So how one thing affects another, but also how it affects the future, more importantly. And then we can encode and embed this logic into automated pipelines, which would then produce like beautiful charts, dashboards, as well as periodical reports and summaries. But the problem of today is not that there is too much data for us to handle. The problem is that the data is so vast and comes from so many different sources so quickly. This makes the logic behind the data, this interplay, very, very complex. And the solution of today is to train a model on historical data, a machine learning model, on historical data, and then let it process current data in real time based on what it had learned. And yeah, so that would be it. So what are some scenarios where you could opt in for a real-time machine learning solution? So the first one is obvious. These are autonomous vehicles. They have dozens of sensors, with some of them producing up to 400 megabytes per second of data. And since it's a 2-ton box of steel moving among people, there are a lot of decisions it has to make sure that everything is running smoothly. Like, should it slow down or speed up? How to react to the car ahead braking suddenly, what to do if a pedestrian is crossing the road. Healthcare monitoring is another such example. Like various different bodily metrics, like heart rate or blood pressure, may have different meanings and interpretations depending on other factors, all of which can change really quickly, and we may need to make a decision immediately. The third example is fraud detection, where you're given an ocean of perfectly valid and legal car transactions, and you need to identify the few which are fraudulent. How do you recognize them? How can you be sure? Can you even quantify how sure you are? The final example is definitely less critical, but something all of us are using almost on a daily basis. Recommendation systems. You have a split second to figure out what your user wants to watch tonight. How do you know that? How do you figure that out? What do you suggest them to maximize engagement? Even what image to show for each suggestion? Hopefully you see that there are some shared properties with all these use cases. There's a lot of data, it's produced every second from various sources, and you have a limited time to react, to do something. In any case, it becomes very difficult to build a deterministic solution for this, so we turn to ML models for help. Now I'd like to close the introduction off with somewhat of a motivational quote, illustrating the need for RTML systems. You can't detect fraud if you only know what happened yesterday, but not what happened 30 seconds ago. In other words, you need access to new information as soon as it's generated, immediately, to be able to make better informed decisions, like authorizing a transaction or blocking it. Okay, so in this part of the talk, I would like to give a little breakdown of an RTML system, how it works, what it's built of, and the architecture. So the first thing you'll need for an RTML system is an infrastructure required to support it. Now, you may not need all the components on the slide for the bare minimum implementation, but there are also many things missing if you want to make a superpowered platform. In other words, this seems like a good middle ground. So first of all, you will need a streaming platform like Kafka. You will need a way for records to enter your system, be consumed by various producers, and then exit the system. Then you will need a persistence layer. You will want to persist all the records, as well as their computed features and model predictions, into a database for future analyses and model retrainings. Speaking of models, you will need a model registry, like MLflow, to track, store, and in general, manage your models. A scheduler, like Airflow, is very useful to automate the periodic work. For example, you can't just deploy a model and call it a day. You need to periodically retrain it on new data to keep its understanding up to date with reality. Finally, you don't need, but you really should have some sort of monitoring setup. It doesn't have to be flashy, but it should give you useful insights about the system itself, like CPU load or latency, as well as the business problem you're solving. Once the infrastructure is set up, it's time to prepare everything for the RTML system. So the first step here is data analysis. Even though you won't be manually identifying the logic behind the data, you will be engineering features which you hope will help the model identify this logic. Besides, data can be very dirty, as we all know, and you will want to check for that and clean it if needed. This is especially important in a machine learning context because let's say you forget to remove the outliers and then generate a report. A person reading that report might still notice that mistake and adjust their conclusions accordingly. But an ML model treats every data point as equally valuable. So you might introduce unwanted biases and issues into the model, or, as this is popularly known, garbage in, garbage out. Likely the most challenging step here is feature engineering. This is a creative process with no correct answer, so you should use your intuition to figure out bits of logic behind the data, and then create features which make this logic easier to spot. An important thing to consider here is that you must be able to recreate these features in real time, equivalently. So if a feature requires aggregating 2 years' worth of data for every single record, it might be difficult to integrate it into a real-time solution. One other thing to consider is that the tools you use here to create the dataset might be way more powerful and way more expressive than the tools you will be using in real time to enrich the data. Finally, the last step is to pick the model architecture for the task at hand. Like, is it a classification problem or a regression problem? Is the data heavily unbalanced? Is interpretability important? Once you have answered these questions and chosen a model, you can create a dataset, train the model, embed it into the system, and start streaming. Speaking of the system, what does the system itself do? Well, the core process of an RTML system is essentially the same regardless of the application. And it's, on a high level, it's fairly simple. Like, first you need to read the records from some source, like a topic, a socket, a file, whatever. Then you need to pre-process them, usually cleaning or transforming them to prepare them for further steps. Once they are ready, you will need to enrich them with additional features. Now, these features may be pre-computed and then just joined with a record, or they can be calculated in real time. Regardless, the purpose of these features is to provide context for the record. For example, if I know that your temperature now is 38 degrees, and I know that it was 38 degrees for the past 2 days, you probably have a fever. It's going to be okay. But if I know that your temperature now is 38 degrees, and it was 37 10 minutes ago, then you probably have a problem. I like to make a distinction between two types of contexts. You have a historical context, which refers to information aggregated over longer periods of time, looking farther back into history, and attempting to capture long-term trends and patterns. On the other hand, you have the current context, which refers to short-term aggregations, which attempt to capture current and recent behaviors. In any case, once the record is enriched, you can give it to the model for inputting, and the result of this is going to be different depending on the model and the task. But whatever it is, in the last step, you'll have to write it out into some sync. So again, a topic, file, socket, whatever. And that's pretty much it. That's everything the system has to do. But there's a lot more the system should do to enable the core process. So as I mentioned earlier, you will want to periodically retrain the model to keep its understanding up to date. For this, you will need to persist records and features so that you have a data set on which to train the model, and so on and so forth, not to go into too many details. So to summarize, for an RTML system, you will need an infrastructure required to support it, the preparation modules for data analysis, feature engineering, and initial model training, the core process of reading transactions, processing them, and writing them out, and the supporting system built around this core process in charge of maintenance. And then all of this sits on top of non-technical requirements, such as the processing speed, compliance with regulations, enabling high availability and fault tolerance, and so on. Okay, so now that we know what an RTML system is and how it works, it's time to get to the main part of this story, which is the road that we took to build an RTML system. Now, the subtitle here is how not to build an RTML system, because the road we took to get there wasn't a straight line as much as it was a zigzag road that eventually got us to where we are now. So for context, this project was done a few months ago, and the task was to create an RTML system capable of processing at least 100 transactions per second, while having an end-to-end latency of at most 100 milliseconds. Now, this doesn't sound too much, like too difficult. There are systems processing way more in way less time. But the catch is we had to do this on a single, moderately powerful machine. So not in a cluster and not in the cloud. Additionally, the features we were computing were very intertwined and complex. So this also increased the expected processing time. So in the beginning, all we had was raw data, dirty, unfiltered, and without context, but also very large, on the order of a few million records. We also have the knowledge of what we want to build, what our end goal is, and that's to build the RTML system. As you can see, there's a pretty big gap between these two, but we can use a backtracking approach. What do we need for an RTML system? We need a trained model to embed into it. And what do we need to get a trained model? We need a data set to train it on. And to create the data set, we need raw data, which we already have, so we're done. Now, as I said, the data was very big, so we couldn't process it with something like pandas or similar tools, and we had to look for something much faster and much more efficient. And we found PySpark, which is just a Python wrapper for Spark, around Spark, and we were very satisfied with the results. Then it was time to pick a model, and we went with LightGBM, which is a state-of-the-art tree-based machine learning model, which also relies on gradients to optimize the fit to data. And once again, we were very satisfied with the results. And now it was time to actually build a system. So on this slide, you can see the first proposal for the architecture, and I'm going to give you a moment to take a look at it while I drink a bit of water. So I'm going to go through this quickly. It's going to change in the next few slides. On the left side, we have a source topic where records come in, followed by a pre-processing module, which writes its results into the next topic. This topic splits into two tracks. The green one below is just staging, so we just save the pre-processed transactions into a database. And the yellow one represents the continuation of the core process. So pre-processed records come in, they are enriched with the historical context from Postgres, and with the current context coming from a faster key value store like Redis. Once enriched, the records are written out into the next topic. The red inference track reads a record from this topic, submits it to the REST API where the model is hosted, receives a response, and then sends the record, the computed features, and the model predictions into the last Kafka topic. This topic once again splits into a few tracks. The red one continues downstream to potential consumers and agents, whoever wants to do something with the results. The blue one below is the persistence track, which saves the record, the features, and the predictions into a database for future use. And the pink one going around represents current context maintenance. So since current context is short-term, like aggregations of the past couple of hours at most, we need to continuously keep it updated so that stale records aren't included in the aggregations and new records are. There are two more tracks on this slide represented with dotted lines that I haven't mentioned yet. It's the historical context maintenance, the purple one on the left, which reads records from the database, computes the new historical context, let's say aggregations of the last year, and saves it back into the database for other components to use. The black one on the right represents periodical model retraining. So again, we read records, features, and predictions from the database, train a new instance of the model, and then update it in the REST API. You can see that this way, the core pipeline has no downtime. So the model, the historical context, and the current context can all be updated in real time without interruptions. And this seemed like a good idea and a good architecture. However, as I said, we used PySpark to create the initial dataset, and we were very happy with the results. So when we found out that PySpark supports streaming, we thought it would be excellent at that as well. This would be especially beneficial because this means we could compute features in real time using the exact same code that we used to create the initial dataset. Unfortunately, PySpark and Spark relies on microbatching, which means records aren't processed immediately as soon as they come to the system, and instead the system waits to collect a few and then processes them all together as if they were a small dataset. This made the whole thing much slower than the required 100 millisecond latency. So we had to get rid of PySpark and replace it with something else. And we found Faust, which is essentially a replica of the K-Streams Java library, just for Python. It provided all the functionalities we needed, so we thought this is the end of our troubles. But there was another issue, because of course there was. So this current context maintenance track was implemented like this, external to the enrichment module, because that was the only way to do it with PySpark. But we're not using PySpark anymore. So we can embed the whole thing into the enrichment module itself. And that's what we did next. And everything was fine, but then we realized Faust is actually not maintained anymore, at least not officially, and that's a problem. If something changes in the Kafka API and the whole thing breaks down, the whole thing might break down because Faust no longer supports it. So we had to get rid of Faust as well and replace it with something else. The process was easier on the inference side of things. We just used a native Python module, that's it. The enrichment side was a bit more difficult, but after some internal research and internal discussions, we found Fling. Now, for us Python lovers in the AI department, writing Java code in a Java framework was a radical decision, but it was one that had to be made. So we learned to use Flink, we set it up, and in a few days we had a working prototype with this architecture. However, just by looking at the slide title, I think you know that this is not the end of the story. When we ran the pipeline, we noticed that we barely got any speed up when compared to Faust. And when we explored a bit, we realized that the inference module is actually the bottleneck. And it makes sense. We were wasting time on this two-way API communication when the model could have been directly embedded into the inference module itself. So that's what we did next. And we ran the pipeline, and we barely got any speed up once again. So we explored again, and we figured out that, again, the inference module is the bottleneck. And it, again, made sense. You see, model execution is very fast, relatively fast. It takes like 20 milliseconds for a fairly big record. So we didn't think to parallelize the inference module. But if you think about it, if every record takes 20 milliseconds and the module is single-threaded, then you simply cannot have more than 50 transactions a second. While we were analyzing this, we also figured out that this topic, the middleman topic between enrichment and inference, doesn't really serve a purpose except for making the architecture look clean and decoupled. So we brainstormed a bit and found a single solution solving both problems. We joined the enrichment and inference modules into a single module, a single Flink module, and embedded the model into it. Now, obviously, there were a lot of issues embedding a Python model into Java code, integrating Java with MLflow, and so on. There were also other issues, like how and when to update the historical context and the model in real time without interruptions, without downtime. Luckily, this architecture allowed us to tackle all of these issues and even implement some extra bells and whistles. Now, there's more to this architecture in reality, but going into any further detail would probably be too much. So this is pretty much it regarding the architecture and the story that I wanted to share. But like any other story and any good story, a story needs to have a message for us, a lesson that we can learn from it. And this is the case of in this story as well. So what did we learn on our road to real-time machine learning? The first lesson is about complacency. You could have noticed that many times during the architecture evolution, we used the wrong tool for the job. It's easy to use a tool or a technology just because you're familiar with it, it is or seems easy, or it's in your favorite language. Sometimes this approach will work. Sometimes adopting a new technology is just not worth the effort. But that's only sometimes. Most of the times, it pays off to use the best tool for the job. If nothing else, then because you'll be ready for when the next similar project comes along. The second lesson is about trade-offs, primarily architectural ones. I personally put a lot of thought and effort into creating the system like neatly and in a well-organized way, but there is a point where functionality takes precedence. Because while a clean and neat architecture is beautiful, a latency under 100 milliseconds is required. So you need to shave off the milliseconds whenever you can. So while I firmly believe that we really should strive to create clean, nicely organized systems, I don't think there's such a thing as a correct architecture. And if there was, its definition would be one that enables us and the computer to do our jobs efficiently. Now, there are many other topics that I could talk about regarding this RTML system, but unfortunately, there's no time in this talk. So if you'd like to know more about them, feel free to catch me after the sessions. For now, that's all for me. So once again, thank you very much for coming to my talk. And if you have any questions, I'd be happy to answer them.
Thank you very much. Just wait for the microphone.
Hi, great talk. Really enjoyed it.
Thank you.
Could you go back to the slide with the final architecture?
Sure.
In the enrichment step, what are these two databases representing?
So the pink one is a relic from the, if you remember, the first transformation when we integrated the current context into the enrichment module. And the purple one, Flink, the way we did it is Flink like initially pulls the historical context and has it in its state. And then externally, we inform Flink, hey, there's a new version of the historical context. So it just pings the database and downloads the new version of the historical context. So then the whole state is within Flink, and it can just use that to enrich the records in real time.
Okay. And tell me, which cloud services did you use for deployment of this?
So as I said, the challenge was to build this on a single machine, not in the cluster and not in the cloud. So that was the thing.
Okay.
Eventually, we did actually deploy this on an internal cluster, so still not in the cloud. But for now, like this initial phase was just to create, let's say a proof of concept on a single machine.
Okay, thank you.
Thank you.
Do you have more questions? Yes?
Thanks. I will fully agree that it's a great presentation. Thanks for that one. It's perfect that we have this slide. Regarding the retraining, did you use the full data set, or you were doing the, incremental learning based on new data?
So we would like fine tune on new data every now and then, let's say on a weekly basis or a monthly, whatever. But then every now and then we would do a full retraining on the full data set so that we reset everything, and sometimes this gives you a bigger benefit to proceed forward.
Thanks.
Thank you.
Sorry, one more question. In the inference phase, the brain-like icon, which service is it?
And that's the model. So as I said, we integrated the joint enrichment and inference services and embedded the model into it. Yeah, that's the like GBM within Java.
Okay, thanks.
Welcome.
Thank you. Do you have more questions? No? Miroslav, thank you very much. It was beautiful. Thank you.
Thank you.